So today we're talking about the Cauchy Riemann equations. So I'll tell you in a nutshell, like last time, we gave the definition, which was that f prime of z naught was the limit as h goes to 0 of f of z naught plus h minus f of z naught all divided by h, right? If this limit exists, then f is said to be differentiable, complex differentiable at z naught, right? So right. So we could say z naught is something like x naught plus I y naught, right? So today I'm going to describe to you a equivalent characterization of this which doesn't use the limit, all right, but instead is based on like happy things from calculus 3. So before we get to that, we first need to address another issue, which is that if we have f, let's say big F, all right, a function from R2 to R2, then f is differentiable at x naught comma y naught if there exists linear L from R2 to R2 such that the limit as h1 comma h2 goes to, actually let me just do h, all right, limit as h goes to 0, but here this h is a vector, okay, it's a vector. H goes to 0 of f of, oh goodness gracious, let me give this a name, let me call this P. I'll call it, just P. F of P plus H minus f of P minus L of H, all divided by the length of H equals to 0. And I said is differentiable, but to be more explicit here, what I'm really saying is real differentiable. We don't always say real differentiable when we're just talking about real variables, but in this discussion it's probably worthwhile. Real differentiability. This is what we mean by real differentiability of a mapping from R2 to R2, all right? And in this case, we write L of H equals to the differential of f at P acting on H. So here, dfp is differential. All right, of f at P. And there's a couple theorems that are easy to prove, which I won't prove, but like theorem, if f differentiable at P, then dfp of H is equal to the following: partial f, partial x, partial f, partial y, multiplied by h1, h2. Or you could write this as the gradient of u, the gradient of v, acting on h1, h multiplied by h1, h2. These are 2 by 2 matrices. And just to be clear, I'm putting f equal to u comma v here. So u is the x component, v is the y component, if you will, of this mapping. And we have yet another name for this 2 by 2 matrix I'm writing. This matrix is called the Jacobian of f at p, right? I mean, technically, this is, I have to evaluate at p, all right? But that's the Jacobian of f. Explicitly, it has the following components: ux, vx, uy, vy. That's the Jacobian matrix of a 2 by 2 mapping. So one theorem that we know from what's called advanced calculus is that if it's real differentiable, then the differential, the formula for it is given by a matrix of partial derivatives. Very, very, very simple to calculate. But the deeper theorem, and this theorem is not a hard theorem. It's basically just taking this two-dimensional limit and like looking at past limits. And if you want the details, they're in my advanced calculus notes. I can find them for you. But it's kind of immaterial to this class. The second theorem, which is super useful, is that if u and v have continuous partial derivatives, at p, then f equal to u comma v is real differentiable at p. So this second result is that continuous differentiability implies differentiability. This requires me about a half hour in advanced calculus to prove it carefully. But it has to do with the mean value theorem in a particular little argument, and I usually prove it for n dimensions. I guess in 2 dimensions it would be a little bit quicker, but anyway, so these are things we have to work with, all right? Here, let me make it a little bit less mystical. Example. Let's see here. So last time we talked about the complex conjugate map, right? F of z equals to z bar, right? So looking at this as a real mapping, we have f of x plus iy, right, equals to x plus iy conjugate, which is x minus iy, right? So you're saying, well, what's the relevance here of what you just wrote about real differentiability in complex functions? Well, every complex function is a mapping from C to C, right? So since the complex numbers is R2, if we have a theorem about mappings of functions from R2 to R2, that has something to say about complex functions, right? Because complex functions are mappings from R2 to R2 as well. Okay? And so I'm just sorting it through here just to give you an example of the notation I was just using. So in this case, you know, in other words, this is the other notation you could use. This is f of x comma y equals to x comma minus y, right? So just to try to make the notation I was using a little bit less abstract, in this problem I have u of x comma y equal to x, and I've got v of x comma y equals to minus y, right? Is this mapping continuously differentiable? So like ux equals to 1, uy equals to 0, vx equals to 0, and vy minus 1, right? Are those continuous functions? Yeah. You're like, but you didn't tell me the point. Well, that's the point. Like, this is true at all points, right? These are continuously differentiable everywhere. And it follows from the theorem on continuous differentiability I wrote at the bottom of the board over here that this mapping is real differentiable everywhere. So therefore, thus f is continuously differentiable on R2, which implies it's differentiable on real differentiable on R2. What's the Jacobian matrix look like? The Jacobian of f, remember? So it is 1, 0, 0, oh, excuse me.
Yeah, -1.
0, -1, yeah. All right. Okay. So we need that as kind of a backdrop for the rest of the arguments I'm going to make here, okay? So what makes complex functions, what makes a complex function special, right? So let's discuss what is special. What's special about f from C to C, right? Which has f prime of z naught existing, right? What's special about a complex differentiable function, which is also, of course, a mapping from R2 to R2? Is it the case that complex differentiability implies real differentiability? What do you guys think? Does complex differentiability imply real differentiability? How are we going to judge that?
I don't know if the I
So what was our criteria for complex differentiability? You guys remember? We can use the Carthy-Adori theorem, right? So complex differentiability, let's say at z naught, just for discussion, gives us that f of z is equal to f of z naught, right? Plus phi of z times z minus z naught. And so what's that mean f of z plus h is equal to? It says f of z plus h is equal to f of z naught plus phi of z times h. That gives us a straight up formula, right? Where what? The limit, oh, and I should have put a z plus h on the phi, right? Z plus h, my bad. Where the limit as h goes to 0 of phi of z plus h, remember,
would it not be 1 minus?
that should be z naught.
Is that Z naught over there?
Oh yeah, I'm sorry. My bad. Thank you.
Okay, well, don't you still pull out, wouldn't it be on the multiple, you have Z naught plus H minus Z naught here, right? Yeah, it's still times H.
Okay. Yeah. H goes to 0. This should be f prime of z naught. This is again by the theorem of Carthy-Adori we talked about before, all right? Now, we need to study the Frechet quotient. What's the Frechet quotient? Well, something I should have probably said back when the start of the lecture is that the definition of real differentiability that I've given for you guys is what's also known as Frechet differentiability. So this thing inside the limit is the so-called Frechet quotient. So to judge real differentiability of a function, what we have to do, at least directly speaking, is to study the limit of the Frechet quotient, right? And if that limit exists and is 0, then hooray! That means the mapping is, in fact, real differentiable. So what's the Frechet quotient look like here for our complex differentiable function? Let's calculate it. So we're looking at f of z naught plus h minus f of z naught, right? And I'm gonna say minus phi of z naught plus h times h. Let's see here. Basically, all of this divided by the modulus of h. I want to come to terms with that. And so what I'm suggesting is that here's my thought is that we should make the L of h, right, to be phi of z naught plus h oh, I'm sorry. I've lost my way here. One second, guys. Audric, this is all your fault. You asked me about that cube root problem before class. You know that. That cube root problem. It messed with my brain. Sorry. I've got no excuses. Except the one I just gave. But all right. I got to be careful here, otherwise I'll get off the beaten track. So here we go. Everything here so far is fine. And what I want to look at is, see, I should have. There's a typo in the notes, is what it is. Okay, so f of z naught plus h minus f of z naught, all right, minus f prime of z naught times h over absolute value of h. I mean, modulus of h, right? So what I'm going to claim is that the differential of f at z naught is just given by f prime of z naught. Zoom out a bit so I can fit things in here. So the question is this a reasonable thing? Is this a linear map? Does this define a real linear map on R2? Yeah, because you can.
Because we said it was real differentiable, right? That's what we assumed.
No, we assumed that this is complex differentiable. The question is, does this formula right here make this df z naught actually a mapping from R2 to R2? Well, let me just write it this way. This is, so let's say f prime of z naught is equal to a plus ib for the sake of discussion, all right? It's given to exist here, right? We're assuming complex differentiability. So these such an a and b exist, and if we write that out, a plus ib, right, times h1 plus ih2, what happens? Multiply it out, you've got AH1 minus BH2 plus I times AH1, AH2 rather, plus BH1, which, if you tilt your head and squint, you can see that that is the matrix A minus B, B, A, times the vector H1, H2. So here I'm using our notation here in the complex plane, which is that column vector H1, H2, we write also as this pair H1 comma H2, which we also write as H1 plus IH2. This is the notation I'm using. But we have to look at it as a column vector if we're going to express it as a matrix multiplication. And so, but you guys remember from linear algebra, once you can write the formula as a matrix multiplication times a column vector, it follows it's a linear map, right? If you can write the formula for a mapping from R2 to R2 as matrix multiplication of a vector, it is a linear map. So, so here we go. We have a linear map from R2 to R2, all right? And what remains to prove real differentiability is what? Is that the Frechet quotient actually goes to 0, right? But look at this Frechet quotient. What do we got here? If we look at the absolute value of this, right? Well, do I do that actually? I guess I don't do that. I do, oh, yeah. That's better. Sorry, I'll stick with my notes. My notes are wise. So my notes say, okay, so what this is equal to is phi of z naught plus h minus f prime of z naught all times h over absolute value of h, modulus of h. So what I did is I traded, see up here, if I subtract f of z naught to the other side, I've got phi of z naught plus h times h. So I did. So I'm trading these two terms for this, and then times the h, of course.
So we have phi of z naught plus h equal to f prime of z naught.
So the equation above I could rewrite as this minus that equals to this. And then I just putting this for that, and then factoring the h out.
Oh, never mind. I was getting confused with the limit. Like if you evaluate that limit, that goes to f prime of z naught, and I was like, isn't that just 0? And I was like, okay.
Well, f prime of z naught doesn't have to be 0 now. Now,
I'm saying if you evaluate the limit of phi, but we're not doing that.
okay. So anyway, what do we have? As h goes to 0, what happens with this expression?
We get phi of z naught plus h, whatever that value is.
So let me call this thing Pac-Man. So the limit as h goes to 0 of Pac-Man, right, is equal to the limit as h goes to 0 of phi of z naught plus h, right, minus f prime of z naught times h over h, right?
Can we not split up the limits inside too? Like limit of the first times the limit of the second?
Well, we could, but this is indeterminate.
Yeah.
But the thing is, this is an indeterminate limit, but what can you tell me about the, well, okay, at this point, what I should do is I should take the modulus of this, all right? So check this out. So I take the modulus of the Pac-Man, right? And that gives me the modulus of this, right? And then the modulus, using property, the modulus of a product is the product of the moduli, right? But what is, when you take the modulus, you get modulus of h over modulus of h, which is otherwise known as 1, right? And so this, as you were just telling me, the limit as h goes to 0, this is f prime of z, right? So this limits to 0. But then by homework problem 19, was it?
Yeah.
Basically, by homework problem 19, this implies that the limit as h goes to 0 of Pac-Man is also 0. See, if we can prove the absolute value of the quantity limits to 0, then the quantity before we took the absolute value also limits to 0. So anyway, thus.
So how do you get over the indeterminate problem? Like just using that theorem, the difference of that theorem?
Mhm. Yeah, and the real problem, the reason that that's indeterminate but not troublesome is because this is something that has modulus 1, right? So it doesn't blow up as you go to 0. It just rotates around the origin, always having length 1, different paths of approach. But anyway, the larger point here is f is real differentiable, and what else? With what? With the Jacobian of f. See, there's a little, so this proves the real differentiability, right? But in the proof of the differential, my claimed differential being linear, we should have noticed something else, right? Which is not only is it, not only is that f prime of z giving me the Jacobian, it's also telling me the Jacobian has a very particular pattern. See, the Jacobian of f has to have the form a minus b, ba, right? But what does that say about the partial derivatives of u and v? Remember what this is equal to? This is equal to ux, right? Vx, uy, vy. A is A, B is B. What equations does this give us? A equals to A. We get ux is equal to vy. Yeah, well, I'll write it this way. Uy is equal to minus vx, yeah. So that's the setting b equals to b.
It should be minus vy. Oh, yeah. You're right.
You can put the minus on either side. These right here, guys, these are the Cauchy Riemann equations. They are a necessary consequence of complex differentiability. Or you can just call them the CR equations. So if our function is real differential, if our function is complex differentiable, right? Then it is also real differentiable, and what else? And the Cauchy Riemann equations have to hold true. All right? Now, can you tell me anything else here while we're at it? Like, you notice this f prime is a plus ib, right? Let's take a second here to appreciate other formulas that we can get from this. Let's relate the complex derivative to the real derivative, right? So as I was saying, we assumed it was a plus ib, right? But now that we compare a plus ib to the Jacobian matrix, what is a equal to? A is equal to ux, right?
Yeah.
So we could write this ux plus I. And what's b? Well, b is equal to vx. So we could write it this way. See that? If f is complex differentiable, then in terms of the real partial derivatives of the function, it's just what? Notice we've got a partial x both places, so we could also rewrite this as just partial x of u plus iv, which is just partial f partial x. So if it's complex differentiable, then the complex derivative is literally just the derivative with respect to x. Another way you could look at it, though. You're like, well, you just used x. You could use y, right? Because notice, like, minus b is uy, right? Let's see here. So what is a in terms of a ux is equal to vy, right? So we could have written vy here, right? Minus iuy. And if you want, you can factor an I out and have partial y of minus I, rather. Am I doing this wrong? Sorry, something feels wrong.
Why don't you just take the partial y?
One sec. I think that was supposed to be plus iy. Vx is
Minus vy.
minus uy?
Yeah, it's v minus vx is equal to uy. So would it be minus uy?
Minus uy, okay. Something feels wrong here, Audric.
You get partial y.
Yeah, I mean, I guess.
You should get partial f over partial y.
V minus I u. So I'm just doubting myself on what we're finding. I wanted that to be a plus, not a minus, but it seems to be a minus. No, there's a minus there. I'm just remembering it wrong. My bad. So that's minus I times partial f partial y. See, because this is minus I times u plus iv, right? So like I squared is minus 1. So if I want to factor an I out of v, I got to put like imagine that being minus I squared. So I factor minus I out. I've got minus I times u plus iv for this term, which gives me minus I partial f partial y. Okay, fine. What I forgot about is in the abstract, it ends up being 1 over the unit. Anyway, let me not blather about that here. Okay, so now that we have all this, great. How does this help us? I mean, you're like, but you're just saying that if it's complex differentiable, then you get these conditions. Well, yes, this gives us, though, a simple condition to check that things are not complex differentiable, right? So, because we have the following logic, right? If complex differentiable, right? Then CR equations hold, right? So, what are the CR equations? What are the CR equations? Well, we need to check UX. So in this problem, example 1, what's UX equal to? It's 1, right? And what's VX equal to? 0. What's UY equals to? 0. What's VY equals to? Well, minus 1 in this case, right? And so is UX equal? Well, UX is not equal to VY, right? Because 1 is not equal to minus 1. What does that tell me? That tells me that the conjugate map, f of z equal to z conjugate, is not complex differentiable. Now, the way I prove it in the previous section is to look at the limit along a real axis and along an imaginary axis, and you see that the different path limits disagree. This is way easier than that, right? You see now, notice what this has freed us from? This has freed us from actually looking at two-dimensional limits. We can just calculate partial derivatives and think, right? Now, let's turn the tables, though, see, because this is nice, right, as a no-go theorem, but there's also a go-go theorem? No. So here's the theorem that we'll use, which is very nice. Theorem, if f is continuously differentiable at x naught plus I y naught, let's say z naught, and the CR equations ux equals to vy and uy equal to minus vx hold near z naught, then f is complex differentiable at z naught. In fact, it's more than that, right? It's actually complex differentiable near z naught. So I can replace that at with a near. What does it mean to say that the complex differentiable near z naught? Well, we had a word for that last time. It was, yeah, if it's complex differentiable on an open disk around z naught, we said it was holomorphic at z naught. And as a further refinement of this theorem, if we have continuous differentiability on a domain, right, an open connected set, and if you have the CR equations hold on a domain, then you get that the function's holomorphic on the domain. So if f real is continuously on domain D and CR equations hold for D on D, then F is holomorphic on D, which is to say that it's complex differentiable throughout the set. Now, this is very nice because continuous differentiability is something we can judge by just looking at partial derivatives. All right? And so we can hide all the two-dimensional limits as sort of a backstory to things we already know. All right? So one of the things that was too difficult for us from a direct limiting argument perspective was the exponential function, right? So let's see if we can look at the differentiability of the exponential function now. So let's see here, example. In some sense, this is our first real example for today. So I'll call it example 1. E2? Fine, E2. F of z equals e to the z. So that's e to the x plus iy. In order to make good on the theorems today, we have to be able to calculate the u and the v for a real function, for a complex function. We have to be able to calculate the real and imaginary parts of the complex functions. So to do that, it's different for different problems, but here it looks like this. So this is e to the x times e to the iy. So, I mean, this is the definition I wrote down. E to the x cosine y plus I e to the x sine y. So you got to identify here, u is e to the x cosine y. V is e to the x sine y. There's no I in the u or the v. These are the real and imaginary parts of the function. What's ux? What's vx? Mm-hmm. So ux is equal to u, vx is equal to v.
And then uy is going to be minus sine.
All right.
Be a plus. No,
And so what do we have?
yeah, we have ux and you have uy minus vx.
Mm-hmm. So lo and behold, we have ux equals to vy and uy equal to minus vx. In other words, CR check. Cauchy Riemann equations hold. Where do they hold? The entirety of the complex plane, right? Which, by the way, is open and connected, therefore a domain. So this shows that, in fact, the complex exponential function is holomorphic on all of C. And not just that, what's its derivative? So thus, f prime of z exists on the complex plane, and what is f prime of z? F prime of z, since it exists, is equal to partial f partial x, which is, well, it's the same thing again, isn't it? I'll write it out. It's, e to the x cosine y plus, exactly, it's just e to the z again. So, surprise, surprise. In the complex case, d dz of e to the z is e to the z. Well, that's a relief, isn't it? Now, you're like, what about the other elementary functions, right? Mm-hmm. So let's see, your example 3. What if you wanted to calculate the derivative with respect to z of, say, sine of z? There's two different ways we could go here, right? We could either use the Cauchy Riemann equations, right? But I would like to emphasize here that we could use calculus. See, because you guys are going to prove the chain rule, right? And we know that this is 1 over 2i e to the iz minus e to the minus iz. So I get 1 over 2i, d dz of e to the iz minus 1 over 2i d dz of e to the minus iz, right? But then by the chain rule, in example 2, 1 over 2i e to the iz d dz of iz, 1 over 2i e to the minus iz d dz of minus iz. What's the derivative with respect to z of iz? By stuff we did last class, this is I. By stuff we did last class, this is minus I. Because we can pull out the constant, and the derivative of z with respect to z is 1. dz dz is 1. Just like dx dx was 1. And what do you got? Well, you got 1/2 e to the iz. Minus and minus cancel, giving me a plus the other term too. Guess what that is? Surprise, surprise, cosine z. So the derivative of sine is cosine. Now, if we did this with the Cauchy Riemann equations, it would have been more work. But we could have done that just the same, right? Let me do another example here. Example 4. What if we had f of z equal to, say, z cubed, right? So that would be x plus iy cubed. Now, of course, you could prove complex differentiability here by just going through the difference quotient, like a la calculus 1, right? But I think it's interesting and fun to kind of do it this way. So this is x cubed plus 3i x squared y minus 3x y squared minus y cubed, using the binomial theorem with a equals to x and b equals to I y. Right? Oh, thank you. Yes, very good. Yep. Okay, so what do we got? Hey, if I made a mistake, it'll show up glaringly here in just a second. Minus 3xy squared plus I times 3x squared y minus y cubed, right? So I'm mostly doing this because I want to give you another example of how to calculate the u and the v. I know we have a better way to do this in terms of calculus from the last class. But anyway, here it is, u and v, right? And you can check ux is equal to vy is equal to 3x squared minus 3y squared. And you can also check that vx is equal to minus uy is equal to 6xy. Yeah. In other words, the Cauchy Riemann equations hold, right? And since the Cauchy Riemann equations hold, the cube function is holomorphic where? Where do the Cauchy Riemann equations hold? Well, they hold everywhere, right? So this is another example where the function's complex is differentiable on the whole complex plane. And what is, what is d dz of z cubed? It's ux plus ivx, right, which is 3x squared minus 3y squared plus I times, well, 6xy, right? Now, check this out. This, we can factor a 3 out. It's 3 times x squared minus y squared plus 2ixy, which is in fact 3 times x plus iy times x plus iy, which of course is no surprise 3 z squared. So complex, the Cauchy Riemann equations are useful, but you also, there is a cost. They require us to get down to real notation, right? The level of real notation. But there's also obviously a benefit, right? Let's see here. So what's next here is this theorem 2.3.10, which says that if you have a complex function which has, on a domain, having derivative 0, it has to be constant on that domain. And we'll prove that next time. And also, there's something a little bit more surprising, which is that if you have a function which is holomorphic and real valued on a domain, it's constant. So there are no interesting real valued holomorphic functions on a domain. Like, this story only is interesting when you've got both real and imaginary parts both being non-constant. So anyway, thanks guys. See you Wednesday.